Exercise 1413 is asking you to write the balanced equation for the reaction of different carboxylic acids. So they give you a few of these here. So this is really more than one problem with sodium hydroxide. And these are really neutralization reactions, which we discussed in chapter 10, where an acid and a base combine to give you water and a salt. Water, of course, is the same all the time. The salt is going to be different in each of these cases. Remember, a salt is just another term for an ionic compound. That's when you have a metal and a nonmetal together, and they have opposite charges. We'll see that in a second. But that's what a salt is. Okay, so the first thing we have to do is take the names they give us of these carboxylic acids and draw them. Then we're going to take our base, and our base they're giving us, it's sodium hydroxide. We'll write out water, and then we just have to figure out what the salt is. Okay, first, formic acid. This is actually the common name. The IUPAC name would be methanoic acid. On a test, I will always give you the IUPAC name. That's the one that's based on that table with the prefixes, infixes, and suffixes that we've learned in chapter 11. So this is really methanoic acid. It comes from the Latin word for ant, which is forma, because this is the acid that red ants inject onto your skin. It's the simplest carboxylic acid. So it's just one carbon. And remember, a carboxylic acid has a double bond to oxygen and then a single bond to an OH. Remember that carbon gets 4 bonds. It only has 3 right now, so that fourth one is just going to go to a hydrogen. So that's formic acid right there. We're going to combine that with our base, which they give us, sodium hydroxide. Do you remember the hydroxide, OH, being a base in chapter 10? Right? We often talked about H plus or H3O plus and OH minus. These were sort of shorthands for acids and bases, right? What's really significant about them are the charges. Acids are things that have positive charge, bases are molecules that have negative charge, and liquids that are acidic or basic are electrically charged liquids. They're liquids that are crackling with positive or negative charge. Well, you can see here that this hydroxide is in sodium hydroxide. And so that's going to act as our base. Okay, so a little callback there. Now, we know we're going to get water. We just have to figure out, you always get water with a neutralization reaction when you add an acid and a base. You just have to figure out what the salt is going to be. And to predict the salt, it's useful to see how you got the water in the first place. So the OH from the base combines with an H from the acid. The acid donates an H plus. The base donates the OH minus. Do you see that when you bring those together, you get HOH? That's really H2O. So that's how we're getting the water, that H2O there. The salt is going to be made from whatever's left behind once you combine those. So let me sort of duplicate these so you can see as I play around with them. If this hydrogen goes together with this OH, that's HOH, that's water. So there's our water. And what's left behind pairs up. That is our salt. You can put that there for the salt. Notice you have your metal, sodium, and you have a nonmetal, which is this oxygen that it's bonded to. And so the oxygen is so much more electronegative than the sodium. It gets a negative charge, the sodium gets a positive charge, and they stick together because of those opposite charges. They're an ionic compound, if you remember from chapter 6. And so and you don't have to draw those charges in, that's just what's making these stick together. So that is how you would go about drawing this balanced equation for this reaction. You can go through it and check that it's balanced, But so long as you're just copying the molecules and moving them around, it will be balanced because you're only working with the atoms you originally had. Let's try another one. Let's try two more, actually, so we sort of build up a sense of confidence with this. With all of these, we're going to have an acid plus a base giving us a water and a salt. That's just what a neutralization reaction is. So let's draw our acid in. Now here they give us this name. When you're going from the name to the structure, you start by looking at the backbone. Notice we have the prefix prop here, that's 3 carbons. So I'm going to draw 1, 2, 3. Hopefully you feel okay with these skeletal structures. AN, that means all single bonds. Oic acid, that means we have a carboxylic acid. Double bond to oxygen, single bond to OH. So that's the backbone, that's propanoic acid. Remember that you always number the backbone to give the functional group the lowest number. And here that's this carboxylic acid here. So we're going to have 1, 2, 3. On carbon number 3, we're going to have a chlorine coming off. And so here we can just have coming off of there a chlorine. So that is 3-chloro-propanoic acid. That's our acid there. We're going to combine it with our base. They give us the base in the problem. They said it's sodium hydroxide, so we'll just draw that in, sodium hydroxide. We know we're going to get water, H2O. We just have to figure out the salt. The water is coming from the H from the acid and the OH from the base. And so the salt will be whatever is left over after those two combine. So the H of this acid will combine with the OH of the base. That's your HOH, that is H2O. And then what's left over combines. So that sodium there will combine with that oxygen, and you can draw that in there, and that's your salt. And you know it's a salt because it's an ionic compound, a metal and a non-metal, sticking together because they have opposite charges there. Okay, let's try one more. Notice it's essentially the same. If you compare what we just did with the first one we did, I know there's a lot of writing on here, but really they're almost exactly the same. The only difference is what the rest of the carboxylic acid is. Right? That green part's the only difference in these two. If you compare everything else here is identical. Right, so just those little things. Really, there's a pattern here. The only thing that's changing is the structure of the carboxylic acid. But how the functional group behaves, that's the same every time. And that's what a functional group is. It's a group of atoms that always behaves or functions in the same way, no matter what carbon chain it's on. So these carboxylic acids will always undergo these neutralization reactions in the presence of a base. Let's try one last one, benzoic acid. This one is a little strange looking, and it's a structure that we didn't have a chance to talk about much in class. It's a 6-membered ring with what look like alternating single and double bonds. That molecule there is called benzene. It's what's responsible for the sweet smell of gasoline, and it's in a lot of hormones and neurotransmitters. By itself, though, that would be carcinogenic. Of course, hormones and neurotransmitters that are made from benzene are not. Benzoic acid has a carboxylic acid coming off of that benzene ring, hence the oic acid. This is so common, this particular structure is so common that you really should know the structure of benzoic acid. So this would be fair game on a test. So make sure you know the structure of that benzoic acid. It's often used actually it might be in some things in your kitchen. It's often used to preserve some foods. We'll see this here. The salt that we're going to get out of here is something that's often put in guacamole and hummus and stuff like that to help preserve it. called sodium benzoate. You can look in the ingredients of like guacamole in your fridge and you'll see it probably has sodium benzoate in it. As far as how you get that preservative, that sodium benzoate, you get it by taking this acid, combining it with a base, and the base they give us, just like before, sodium hydroxide. They gave it to us in the problem. This is a neutralization reaction. How do you know? Because we're combining an acid and a base. You combine an acid and a base, they neutralize each other. The positive charge of the acid cancels out the negative charge of the base. They neutralize each other. And a neutralization reaction always gives you water and a salt. So we know water is always H2O. We just have to figure out what that salt looks like. Where are you getting the H2O? The acid donates an H+, the base donates the OH-. So the salt is just whatever's left over after those two combine. So here we can see the H of the acid combining with the OH of the base. That gives us our HOH, or our water, H2O. And then what's left over, the sodium, combines with that oxygen there that lost its hydrogen. And that's called sodium benzoate, this molecule here, sodium benzoate. And it is very, very, very slightly toxic. So it's deadly to microbes because they're so small, but our liver can detoxify it and pump it out of our blood into our urine before it does damage. So it's used to preserve foods, especially foods that have oils in them, like hummus or guacamole. Notice again, if you compare this to the last one, the process of going through this is almost entirely the same. You have that carboxylic acid and NaOH, you have water, and it just turns into that ONA. And the only difference is what else is hanging off of that original carboxylic acid. So carboxylic acids are acids, and so it's an opportunity to think back to the stuff we learned about acids in Chapter 10 and how they can react with bases to cancel each other's charges out to give you water and a salt.